All right, in this podcast, we're going to talk about buffer pH. Okay, so we've already talked about the fact that buffers are going to be your weak acids with the salt of the conjugate base, or you could even have a weak base with the salt of the conjugate acid. All right, so if it's a very weak acid, then it's going to have a higher pH value. We already know that. And then if it's a very strong acid, obviously it's going to have a lower pH value. All right, so last podcast we talked about how we identified buffered solutions. All right, so if you look through the list here, let's see which one of these are actually considered buffered solutions. So you can do this one of two ways. You can either look at the change in pH, or you can actually just try to look at the actual thing. I'm going to start with a change in pH. So we don't want our pH to change more than 1 pH point. So that pretty much eliminates this one completely, and this one, and this one. So that basically leaves us just with these last two, which makes sense. It's the weak base with the conjugate acid in this case. And the next question is looking at the concentrations of them. So the most effective buffers are the ones that can resist changes in pH when we add acids or bases to them. So in order to do that, they have to have a higher concentration. The ones that are going to equally are going to resist changes in both acids and bases at the same equivalent is when they have the same concentration. So you want your acid to have a very close conjugation to the conjugate acid, or the reverse if you're talking about a weak base. So we need these to be pretty close so that they can handle the same amount of acids and bases added. So if I add 3 moles of acid or 3 moles of base, either way, my pH is not going to shift very much because that's a very effective buffer. All right, so how does the actual ratio between these two affect our pH? So remember that we have the Henderson-Hasselbalch equation, which is defined by the pKa, and then the log of the ratio of the conjugate base over the acid. Okay, so, or obviously the opposite if we were talking about a weak base, right? So I will go ahead and put that down here too, just in case you need to know that. So this would be HB plus and just B down here. Okay, all right, so now let's go up here and look at how our ratios, so it gives us the ratios in these 3 cases, and then it tells us what the pH is. Okay, so my first question is, well, what's the pKa or pKb in this case, right? So, because this is a situation where we're looking at weak acid, okay? Weak acid and the conjugate base. So we know that when these two values are equivalent, that this basically cancels out and pH is equal to pKa. So by looking at our data, we can tell that 6.36 is our pKa. So it appears as if our ratio is less than 1, then we are going to decrease our pH, okay? So pH goes down. All right, and then if we have a ratio higher than 1, our pH goes up from the pKa. All right, now this is something else I wanted to touch on, make sure you guys understood. When we create a buffer solution, we definitely are having a common ion effect occurrence. So say I have the weak acid, acetic acid, it makes this conjugate base, right? If I throw in a salt that has that conjugate base in it, okay, what it does is it shifts the equilibrium of my acid. So it shifts my equilibrium of my acid to the left and actually makes the dissociation even lower than it previously was. So it kind of makes the acid weaker in a sense. All right, and then conversely, the opposite is true for bases. So if I have a weak base and there's my conjugate acid, and then I throw in a salt that has that conjugate acid in it, it is going to cause my equilibrium to shift back to the left, which is going to decrease the amount of my weak base that is dissociating. Okay, so like I said, again, that all brings us back to the equation, pH equal pKa. So we can make some generalizations about what's going on if we know what our pKa is and what our pH of our solution is. So if our pH is less than our pKa, what that tells us is that we have more acid. If our pH is greater than our pKa, that's telling us we got more base. All right, so here's an example. So in this example, a buffer solution was created by mixing HCO. Okay, and there's a typo here, so I did want to point it out to you. All right, so this little 2 right here, 3, it should have been a 2. So that was a typo on my part. Apologize. All right, so the final pH of the solution is 2.89. And we know that our Ka is 1.8 times 10 to the negative 4th. We want to know which one of the species has the higher concentration. So we know our pH. We need to find our pKa. So to get our pKa, we're going to negative log the 1.8 times 10 to the negative 4th, which is going to give us 3.74. Okay, and so what that is telling us is that because our pH value is less than our pKa value, that means that we have more acid. So here's the acidic species, so we definitely have more of that.